Hi, Stu Schwartz from MasterMathMentor.com. This is video AB17b. The topic is straight line motion, and it covers the AB manual pages 97 and 98. In our previous study of straight line motion, we concentrated on motion on the horizontal. We were given a position function and calculated the velocity and acceleration functions by using the derivatives. The same rules apply to motion in the vertical direction, but there is now one more factor in the mix: gravity. Whenever an object is moving up or down, it is subjected to gravity. Isaac Newton developed a law of universal gravitation in the year 1687. When we are discussing particle motion in the vertical direction, there are some variables we usually use. V0, which is the same as V of 0, is the initial velocity. It refers to how fast our object is moving when we start the process. S0, which is the same thing as S of 0, is the initial height. It is how high the object is off the ground when we start the process. Our position function is called S of t. Its sign interpretation is, if it is positive, the position is above the initial height. If it is negative, then the position is below the initial height. If we are working in feet, our formula for the position function when subjected to gravity is S of t equals negative 16t squared plus v0t plus s0. If we are working in meters, then our position function is given by S of t is equal to negative 4.9 t squared plus v0t plus s0. On the AP exam, you will probably be given these formulas. Your teacher may require you to memorize them. You may wonder where these formulas come from. In the second half of the course, when we discuss integral calculus, we will actually evolve these formulas. Velocity is v of t. Its sign is interpreted: if velocity is positive, then the object is moving upward. If the velocity is negative, then the object is moving downward. The formula is, for feet, v of t is equal to negative 32t plus v sub 0 measured in feet per second. That is simply the derivative of s of t. Working in meters, v of t is equal to negative 9.8t plus v sub 0. That would be measured in meters per second. Acceleration is labeled a of t. A positive acceleration means the object is accelerating upward, and a negative acceleration means that the object is accelerating downward. For feet, a of t is equal to negative 32 feet per second, or feet per second squared. This is the force of gravity. It is negative because gravity pulls an object downward. Working in meters, a of t is equal to negative 9.8 meters per second, or meters per second squared. When an object is thrown upwards, it has an initial velocity v0. As it gets higher and higher, gravity works on it until its velocity is 0 when it reaches maximum height. So, to find the maximum height of an object, set the velocity equal to 0, solve for t, and then find s of t. When an object falls from maximum height, it has an initial velocity of 0. As time goes on, the velocity gets more and more negative because the speed increases. When the object hits the ground, its final position is s equals 0. So to find the velocity of an object when it hits the ground, set s of t equal to 0, solve for t, and then find v of t. In problem number 5, you were told that a ball is launched vertically from ground level with an initial velocity of 112 feet per second, and there are 3 questions that are asked. In A, we're asked to find the velocity and speed of the ball at t equals 3 and t equals 5 seconds. Since the initial position is the ground, S0 equals 0, and S of t is equal to negative 16t squared plus 112t. Therefore, V of t is the derivative of S, which is negative 32t plus 112. Finding the velocity at 3 seconds, we get 16 feet per second, and the speed is also 16 feet per second. The velocity at 5 seconds is negative 48 feet per second, and therefore the speed is 48 feet per second. Since v of 3 is positive, the ball is still on its way up at 3 seconds. Since v of 5 is negative, the ball has reached its height and is now on its way down at 5 seconds. In B, you're asked to find how high will the ball rise. So we take our velocity, which is negative 32t plus 112, and set it equal to 0. Therefore, 32t equals 112 and t equals 3.5. So it takes 3.5 seconds for the ball to reach its high point. Therefore, we find S of 3.5, which is negative 16 times 3.5 squared plus 112 times 3.5, and therefore we get that the ball reaches a height of 196 feet at its maximum. In C, we're asked to find the speed of the ball when it hits the ground. So using our S of t, which is negative 16t squared plus 112t, we set that equal to 0. We can factor out a negative 16 and we get negative 16. Quantity t minus 7 equals 0, and therefore t equals 7. Therefore, v of 7 is equal to negative 32 times 7 plus 112, which is equal to negative 112. So the absolute value of v of 7 is 112 feet per second. In general, the speed that an object leaves the ground will be the same as the speed that the object hits the ground. In 6, we are given equations for free fall on Mars, Earth, and Jupiter, where S is in meters and T is in seconds. We'd like to know how long it would take a piece of equipment that was dropped from some height to reach a speed of 44.7 meters per second, which is 100 miles per hour. On Mars, S of t is equal to negative 1.86 t squared. So V of t is equal to negative 3.72 t. And the absolute value of V of t is 3.72 t, which is set equal to 44.7. So it takes 12.016 seconds for an object to reach 100 miles per hour. On Earth, S of t equals negative 4.9 t squared. So V of t equals negative 9.8 t. The absolute value of V of t is 9.8 t, which is equal to 44.7. And therefore, on Earth, it takes 4.561 seconds for the object to reach 100 miles per hour. On Jupiter, S of t equals negative 11.44 t squared. So V of t equals negative 22.88 t. And the absolute value of V of t is 22.88 t, which is equal to 44.7. So t is equal to 1.954 seconds. This shows that Jupiter has a much greater gravity than Earth and Mars. Finally, it's important to understand that the object itself makes no difference in its calculations. Whether it is a penny or a bowling ball, the amount of time it takes to hit the ground is the same. 7 reads, a rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second reaches a height of S of t equals 24t minus 0.8 t squared meters in 10 seconds. There are 6 questions that are typically asked in a calculus setting. A asks to find the rock's velocity and acceleration as a function of time. So v of t is equal to 24 minus 1.6t, and a of t is equal to a constant negative 1.6. Question B asks how long did it take for the rock to reach its highest point? We take v of t and set it equal to 0. So 24 minus 1.6t equals 0, and t is equal to 15 seconds. Question C asks how high off the surface of the moon does the rock get? Since we know it took 15 seconds to reach its high point, we calculate S of 15, which is 24 minus 15 minus 0.8 times 15 squared. And our answer, S of 15, is equal to 180 meters. Notice that we do not put in the units until the very, very end. D asks how long did it take for the rock to reach half its maximum height? Be careful, the answer is not half of 15 or 7.5. We take 24t minus 0.8t squared and set it equal to 90. 0.8t squared minus 24t minus 90 is equal to 0, and either by the quadratic formula or using your calculator you get t is equal to 4.393 seconds. At first, the rock is going much faster and therefore reaches its maximum height relatively quickly. It slows down because of gravity. E asks how long was the rock aloft? So we take the S formula and are interested where S is equal to 0. 24t minus 0.8t squared is equal to 0, and we get 8t times the quantity 3 minus 0.1t is equal to 0. And obviously t is equal to 0, that's when we started, and t is equal to 30 seconds. When an object is thrown from the ground, straight up and then hits the ground, it will take the same amount of time that it takes going up as it does going down. So we could have doubled the answer in B, 15 seconds to get 30 seconds. F asks to find the rock's speed when hitting the moon. We find v of 30 to get 24 minus 1.6 times 30, and v of t is equal to negative 24, and the speed is 24 meters per second. That's the same speed that it had when it left the moon. In number 8, we're told that a ball is dropped from the top of the Empire State Building, which is 1,250 feet high. We would like to know how long it will take to hit the ground and also to find the speed at impact. Hitting the ground means that S of t equals 0. The formula for S is negative 16t squared plus v0t plus S0. There is no initial velocity because the ball is dropped, and the initial height is 1,250. So negative 16t squared plus 1,250 equals 0, giving 16t squared equals 1,250, and therefore t equals 8.839 seconds. B asks to find the speed at impact. V of t is equal to negative 32t. So calculating that when t equals 8.839, we get 282.843 feet per second, which is approximately 193 miles per hour. Actually, the ball will not reach that speed because it will reach what is called terminal velocity. Because of air resistance, the ball cannot get faster than a particular speed. You will learn about this if you're taking a physics course. The last two problems deal with generic straight line motion. Number 9 reads, a particle moving along a straight line has position function s of t equals the natural log of t squared minus 2t plus 2. We would like to know what is the particle's velocity when it has no acceleration. Our game plan for this problem is to first find the velocity, then the acceleration. We're going to set the acceleration equal to 0 and find the values of t that make this true, and then plug those values back into the velocity function. So v is equal to 1 over t squared minus 2t plus 2 times 2t minus 2. We're going to have to take the derivative of that, so we'd like to simplify that as much as possible, and we'll factor out the 2 and get the quantity t minus 1 over t squared minus 2t plus 2. We have to take the derivative to get the acceleration, and we have a quotient rule. We square the bottom, and then upstairs we get t squared minus 2t plus 2 minus the top, t minus 1, times the derivative of the bottom, 2t minus 2. Some algebra is done to get this into factorable form and set equal to 0, and we get t equals 0 and t equals 2. So we then go and plug 0 into the velocity function and get negative 1, and we plug 2 into the velocity function and get 1. Notice that no units were mentioned here, so no units are given in the answer. Number 10 is a good calculator problem, and you will be tested on your ability of using the calculator. This problem can be done by hand, but the amount of work that it would create is enormous. The calculator can do the problem quite quickly. It reads, a particle moves along the x-axis with position function s of t equals sine of e to the 0.5t. Use your calculator to determine at which of the integer values t equals 1, 2, 3, 4, or 5 is the particle to the right of the y-axis and speeding up. Explain your answer. We now put the position function, velocity function, and acceleration function into the calculator. y1 will be the position function, sine of e raised to the 0.5x. We could use our trig and chain rule to find the velocity function, but why not let the calculator take it? So y2 is n deriv of y1 comma x comma x. The same thing is true with the acceleration. We'll let y3 equal n deriv of y2 comma x comma x. This technique is a good one, especially if you do not have to show the work in calculating these derivatives. We will now use our calculator's table ability. Realize first that your x values are really your t values. We first go to table set and set table start equal to 1 and delta table equal to 1. We then go to our table and we will see our x values along with our lists y1, y2, and y3. You can only see 2 of these columns at a time, and you'll have to scroll over to get the third one. I show all 3 in the table on the screen. So what does this table tell us? Remember that the x values are really t values. We would like to find out when the particle is to the right of the y-axis. That means that y1 must be positive. That occurs from t equals 1, t equals 2, and t is equal to 4. We also want the particle to be speeding up. That means that the velocity in y2 and acceleration in y3 must have the same signs. That occurs at t equals 1, and t is equal to 2, and t is equal to 5. So only t equals 1 and t equals 2 meet both criteria. We are not finished with straight line motion. Later in the course, we will revisit the topic when we have a velocity function and we would like to get some idea of how far we have traveled between two times.